Thank you for having us in your conference, long distance and all. We hope that our format will work. It is experimental. This conference aims to cross over discard studies and STS. We, you see us there, work on that crossover as well. But we add a third source of inspiration, valuation studies. This interdiscipline engages in inquiries of worth. It wonders what is locally enacted as good or as bad in one version of good and bad or another. How to attend to the goods and bads to do with discards in an STS-informed way. Today, we will give you a taste of that. Our examples come from our fieldwork into wastewater in the Netherlands and the various attempts to deal with this. We hope to convince you that at the crossroad between STS and discard studies, attention to valuations, that is, to valuing, is crucial. To this end, we will open up some of the ways in which things are locally valued, that's to say judged, measured, appreciated and or cared for in the wastewater world. Here, for a simplified, catchy lead for our talk. Earlier STS called upon us to follow the actors. Discard studies set out to follow the stuff. And here we argue that it is worthwhile to follow the problem. The problem? Not quite. For as one tries to follow it, the problem shifts and changes, or there appear to be many problems in the plural. As in our field we were trying to follow the problem, we quickly noticed that there are actually far too many to count, and they pop up everywhere. Such complexity cannot be easily caught in a talk. A talk tends to only work if it's fairly straightforward and relatively simple, like our catchy lead. So, what to do? What we try today is 1. Give you a more or less straightforward narrative, and then 2. Add sidelines. The sidelines are not less relevant than the central line. Instead, we hope to convey that sidestepping the linearity between problems here and solutions there is essential to understanding problems. Wastewater problems in our case, but many other problems too. Our catchy lead, as well as the rest of our analysis, obviously built on the work of many others. The call to follow the actors was meant as an alternative for an earlier understanding of science as a collection of theoretical propositions representing reality. The call was instead to study science as a matter of practices interfering in reality. The actors to follow were the people, other creatures, and entities relevant to science practices. As one studies technologies, this is all the more obvious, as technologies are never meant to represent, but always already to interfere. Interfering, as in, hopefully, improving. Interfering, as in tackling problems. And who knows, maybe solving them. A crucial concern of one of our other ancestors' discard study is that discarded stuff endures. Discards may be cleaned away from one site, but that does not mean they disappear. Decades ago, Mary Douglas famously wrote that dirt is matter out of place. If you wipe sand out of the house into the garden, it is no longer dirt. The shortest possible summary of the contribution made by discard studies is to say, most discards are not like Douglas dirt. They remain bad, even when they're tidied away. Take a plastic bottle. Once discarded, it is out of place everywhere. This has to do with what it does. Wherever it goes, discarded plastic is bound to form an ecological problem. This suggests that, as a next step, what deserves attention is how and where are discards of all kinds a problem? And what kind of problem? And how is this valuation that something is a problem being made?
Our field is that of wastewater. In this field, plastic and other persistent kinds of stuff are obnoxious too. But the first kind of discards that form a problem in wastewater readily transforms: poo and pee. The organic leftovers of human metabolism, excrements. Through a tragic twist of history, excrements are carried out of our houses with water. Instead of compost bin systems, we have sewage systems. The sewage system was designed in the 19th century to solve the problem of infectious diseases, most notably cholera. Cholera spread in sites where drinking water was polluted with bacteria residing in human bowels. Sewage system allowed for a separation between what goes into human bodies, drinking water, and what goes out of human bodies, pee and poo. In the process, the water used to flush out water closettes became wastewater. Water that carries waste along with it. In water, the organic materials in urine and feces gets eaten by living creatures. Ideally, like in a compost heap, they would then re-enter the metabolic cycles from which they emerged. However, over time, as the numbers of people linked to sewage systems grew, so did the concentration of excrements. The microbes downstream started to grow in such large numbers that they used up so much oxygen in the water that other creatures, such as fish, died off. Algae blooms, in addition, took away the light from other species. Surface waters turned into ecological deserts. Hence, even though microbes and algae metabolized excrements, they formed a problem. Solving the problem of epidemics with sewage system created a problem for the organisms that lived in the water downstream.
And here's for a sideline. This is to flag up that technical solutions themselves usually come with problems too. They need to somehow function, and that's rarely friction-free. In the case of sewage systems, in flat countries like the Netherlands, pumps are needed to transport sewage from houses to wastewater treatment facilities. Fat from cooking and soap or wet wipes flushed down the toilet may block pipes. Furthermore, rats live in sewage pipes, and if there are any cracks, they may enter houses through them. And sewage pipes do not endure endlessly. They require a lot of maintenance work.
Back to the main trail of our story. Solving one problem tends to create another. Sewage systems solved the problem. There's no more cholera in cities with good sewage systems. They created another problem along the way. Life downstream suffers. It is to tackle that problem that wastewater treatment plants were built. In these plants, microbes can go ahead and eat the organic materials present in the sewage without disturbing other organisms, like fish, for they don't live there. In different basins, optimal conditions are created for different kinds of microbes. Some hold a lot of oxygen, others hardly any. The idea is to ensure that as many organic material as possible is digested and incorporated by the many species of microbes that are around. The excess of microbes is taken out of the basins. In this way, the nutrients that were present in the excrements are removed from the waters that flow out of the wastewater treatment plant and into surface waters downstream. Again, a problem solved, or almost. Ongoing tinkering is required, as populations keep growing while the technology itself needs constant care. But as it is, in the Netherlands at least, algae blooms are far less frequent and there tends to be enough oxygen in surface water for at least part of the species that are welcome there. The most prominent problems created, this time, have to do with the greenhouse gases that the microbes produce. As they digest excrements, they produce methane and CO2.
Another sideline here. As ever more excrements flow in, the microbes keep on growing. To prevent the problem of overfill basins, some are taken out. Then they are fermented through anaerobic digestion, which produces methane that can be used for fuel, for energy. The residues that remain after fermentation are burned in waste incineration. These processes provide energy that can be used in the wastewater treatment plant. Two problems solved: the excess of microbes and the energy needed to pump wastewater around. However, burning anything pollutes the air. In this way, diminishing water pollution comes at the cost of increasing air pollution. An added complexity for those grappling with this problem is that these two kinds of pollution come with different accounting systems, knowledgeable engineers, and responsible authorities. And there is more. Another tragedy revealed here is that the nutrients that the excrements contained are taken out of the metabolic cycles. Especially the phosphorus involved is precious. Global supplies of phosphorus are limited, and mining phosphorus is a nasty affair, destructive for the ecosystems in the sites where the mines are located. The engineers in our field, therefore, work on technologies that might reintroduce metabolic circularity. Some, for instance, try to use algae to metabolize excrements. These are less likely than bacteria to carry infections along to human bodies. Others encourage magnesium and phosphorus to crystallize into struvite. No pathogens there either.
But well, one problem may also hide another. While algae and struvite are unlikely to contain pathogens, they might contain toxins. Where before we saw that solving one problem can create another problem, here, solving one problem reveals another problem, makes it visible, apparent. Which is, in this case, that humans do not just excrete the remnants of the foods they've eaten, they also excrete metabolites of the medicines and drugs they take. Added to that, people do not just flush out their poo and pee. They also flush out the bleach they use to clean their toilets, the soap they use to wash their floors and bodies, the microplastics shed by their clothing, and so on. These added discards are potentially toxic and therefore not welcome in our foods. They are also not welcome in surface water. Earlier, their presence in surface water went unnoticed. If fish die from lack of oxygen and/or light, then that problem was to be addressed. It is only when it appears that fish still do not thrive, even if there is more oxygen and more light, that the question arises what else is going on. It doesn't help that the toxins in question are not very easy to detect by looking or smelling. Their concentrations are not particularly high. In the wastewater treatment world, they're currently called micropollutants because, at least so far, their presence in wastewater is measured in micrograms.
Once again, we're at a sideline here, this time about the toxicological logics behind the problem of micropollutants. Until recently, the idea was that stuff present in low concentrations doesn't harm anything or anyone. The doxa in toxicology was that harm increases with concentration. Low concentrations, even of the stuff that is toxic in higher concentrations, were deemed to be unproblematic. More recently, however, this doxa has suffered severe blows. For once, some substances appear to be disruptive even at very low concentrations. A case in point are the estrogens present in contraceptive pills. Even in extremely low doses, they induce changes in genetically male fish that hamper their ability to reproduce. This causes problems for fish populations. And then, new research has put new problems on the agenda. Another blow to the vested idea that low concentrations are unproblematic is that some micropollutants are stable. They do not fall apart, or if they do, they take a millennia, not decades. This means that if they're allowed to continue leaking, their concentration is bound to gradually increase. In this way, sooner or later, they will become a problem. And the more toxic they are, the sooner this is. Future problems may deserve to be put on present-day agendas too.
If solutions create problems, then different solutions create different problems. Back to the main trail of our story. As the problematic character has become apparent in the wastewater treatment world, micropollutants are currently on the agenda. Various technologies are put to use to deal with them. Here's for two examples, a bit quick and simplified. For one, in some Dutch wastewater treatment plants, ozone is used to break down micropollutants. This ozone treatment indeed helps to lower the concentration of quite a few micropollutants in the effluent, at least as far as they happen to be measured. However, due to the ozone, bromide present in the wastewater is unduly transformed into bromate. Bromate happens to be carcinogenic and is therefore on the list of forbidden substances. Another technique used to retrieve micropollutants is that of adding activated charcoal to the water in the treatment plant. Micropollutants get caught in small pores in the charcoal. Hence, this technique lowers the concentration of micropollutants in the effluent. However, there's a catch once again. In the process of sourcing activated charcoal, ecologies this charcoal is taken from are upended. And the activation process also comes with significant carbon emissions. Furthermore, processing the charcoal after it has done its job comes with air pollution issues of its own. The point is clear. If solutions create problems, then different solutions create different problems.
It is important to note, and that is why we mention it in the present sideline, that none of this is our own discovery. Everything we are telling you today, we learned from the wastewater engineers we work with. If policymakers might sometimes suggest that all ecological problems have technical solutions, not so for the engineers involved. Water engineers don't believe in technical fixes. They know fully well that every technical solution here is bound to create another problem there. They also know fully well that solving problems is not a matter of weighing pros and cons and then making a firm decision of a few technical trajectories. For making decisions is fine, but what matters most is getting things done in practice. One of the conundrums at this point is that in getting things done, this or that solution takes a concrete, literally concrete, and also metal shape. The technologies involved cost a lot and they will endure for quite a while. As one of our informants told us, we would like to tinker with the ozone and the activated carbon for a bit, see what works best, and try out alternatives. But the policymakers are eager to show that they are on top of things. They have set apart the necessary money, and this money must be spent now or say in the next 2 years. The haste tied to many a policy decision helps to consolidate, to materially fixate technologies that may not be quite there yet. Bureaucratic problems make tinkering with technical problems even more difficult than it already is.
Let's now turn to the micropollutants then. First, PFAS. So far, we took you to the wastewater treatment plant, taking that as the entrance point of our story. In our research, this is one of our entrance points too. We have visited wastewater treatment plants, interviewed wastewater engineers, attended their conferences, and looked into their technologies at stake. But there are more ways to enter the entangled worlds of discards, technologies, and valuation processes. One such way is to attend to the stuff that ends up in the water as micropollutants. One of the polluting substances that stand out as particularly contentious at the moment is PFAS. Or rather, this is not a single substance, but a large group of molecules that include bonds of fluor and carbon. PFAS make pans non-sticky and raincoats water repellent, and have a range of other such practical uses. In all these uses, PFAS have been hailed as a solution to a problem. This does not help address concerns about problems to do with the toxicity of PFAS. How to mitigate those problems? Unlike organic materials, PFAS cannot be digested by microbes. They hardly break down at all. As ingesting PFAS via drinking water harms human health, PFAS is filtered out of drinking water. However, this means that the residue water contains higher concentrations of PFAS. This PFAS-containing water flows out with the effluent of drinking water purification plants. The cleaning of drinking water comes at the cost of increasing the concentration of PFAS in surface water. Land that contains some variant of PFAS can sometimes be cleaned by plants. Hemp, for instance, absorbs PFAS. This particular kind of eating, however, does not involve a chemical transformation. It is not a matter of digesting, just one of storing. If the hemp would be left to decay in the fields, the PFAS would seep into the soil again. We came across a project where the hemp is used as building material. In this way, it is enclosed and will not come out. For as long as the building lasts, the problem is contained.
Again, we can add further complications, hence this sideline. What the case of PFAS helps to articulate is the different registers in which something is or isn't defined as a problem. As drinking water companies filter out PFAS, they solve or prevent health problems of the humans, pets, and others who drink their tap water. At the same time, they also solve a legal problem. They abide by regulations to do with the amounts of various toxins in drinking water. They'd get fined if they didn't, but in doing so, they consolidate the ecological problem that PFAS harms downstream species. For instance, they disrupt the reproduction of the indicator species water fleas. As the health problems and then legal problem are solved by taking PFAS out of drinking water, PFAS accumulate in riverbeds and continue to build up over time. Addressing present-day problems thus takes precedence over attending to long-term problems that are, as of yet, not so clearly defined.
And now, on to another type of micropollutant, the pharmaceutical. The case of pharmaceutical helps highlight what at face value may seem like one problem is likely to form a different kind of problem for different human actors, depending on where they are situated. At a conference about micropollutants, a number of wastewater experts insisted that water authorities cannot tell doctors which medicines to prescribe or patients which medicines to take. Therefore, they said, we simply have to do what we can and develop cleaning techniques that retrieve the remnants of medicine from wastewater. Eco-minded doctors, in their turn, are concerned about overprescription. They insist that both patients and ecosystems suffer from the excessive amount of drugs currently prescribed, and they seek alternative solutions for health problems like walking, talking, and swimming. Toxicology researchers, in their turn, try to find out which drugs are more and which are less polluting for ecosystems. Drug designers, finally, seek to design medication that work inside the patient's body, but once excreted, rapidly become inactive. Hence, in this case, as the ownership shifts, the problem also transforms.
One last sideline. You are an STS audience, so measurement. The problem at the center of our talk is that of wastewater, of the way surface water is dirty due to both organic remnants of human digestion and other stuff, here called the micropollutants. But policymakers and engineers tend to want their problems operationalized and quantified. And this comes with another avalanche of complexities. We could easily fill an entire talk with this issue alone. But here is just a taster. It is possible to do chemical measurements. Measure the concentrations of obnoxious stuff. That is to say, this is not only possible, it is also legally required. A lot of regulations are tied to chemical measurements. There are legally set standards for the maximum allowed concentrations of a range of molecules. However, water plants and fish downstream do not measure stuff, one substance at a time. They dwell in and absorb this or that cocktail of a variety of chemicals. To measure the effects of such cocktails, biological measurement techniques have been developed, the so-called bioassays. They work with indicators, exemplary living creatures or cells thereof, and assess how these respond to effluent of treatment plants and water in other sites. Bioassays are better attuned to what matters to living organisms downstream, but fit less well with the need for uniform regulations that facilitate governance. And finally, it is possible to investigate an ecosystem of interest, a river downstream or the land surrounding it. But which species, how many, how much diversity, and how much complexity to include? Well, that finally is a truly specific local affair. The most relevant and the most difficult to do, let alone to use in a policy context.
To wrap up and conclude, what happens when, as researchers, we follow the problem or the many problems in our fields? We did not offer you solid facts or something like a passepartout theory, but we hope that our call to follow problems is inspiring for your research. Maybe there too, it makes sense to follow problems that accompany or follow on from solutions. Problems that play out in another plane, make sense in another logic, emerge when you move to another site. Problems that hide behind other problems that are bigger, more visible, and easier to smell. Problems that are more readily apparent given the knowledge practices in place. Problems with different facets and faces related to what different actors involved in different practices can do. When faced with an urgent problem, the response is often to think straight, on to the solution. And that may be necessary in the heat of the moment. But we suggest that for STS researchers, it is worthwhile to take a step back, or should I say, a sidestep. Not so as to find some high ground from where it is possible to critique one's field, telling how everyone there falls short of meeting this or that firm value, but instead to wonder how valuing is being done in the practices we study. What emerges as good and what as bad in these practices? What is a problem? What is a solution? For whom? In which way? In addressing such questions, it may help to let go of linearity. That is why in this talk, we also experimented with sidelines and made complexities apparent. And here is for a last caveat. That there are no perfect solutions is no reason to stop trying. We rather admire how the engineers and other experts in our field tenaciously tinker and tinker and tinker again. Even if problems cannot be solved, they can be recognized, measured, shifted, grappled with. They can be faced. Thank you.